In contrast, the wild ancestors of most Southwest Asian crops and animals were absent from Western Europe. Thus, it seems clear that food production did not evolve independently in Western Europe. Instead, it was triggered there by the arrival of Southwest Asian domesticates. The resulting Western European farming societies domesticated the poppy, which subsequently spread eastward as a crop. Another area where local domestication appears to have followed the arrival of Southwest Asian founder crops is the Indus Valley region of the Indian subcontinent. The earliest farming communities there in the 7th millennium BC utilized wheat, barley, and other crops that had been previously domesticated in the Fertile Crescent and that evidently spread to the Indus Valley through Iran. Only later did domesticates derived from indigenous species of the Indian subcontinent, such as humped cattle and sesame, appear in Indus Valley farming communities. In Egypt as well, food production began in the 6th millennium BC with the arrival of Southwest Asian crops. Egyptians then domesticated the sycamore fig and a local vegetable called chufa. The same pattern perhaps applies to Ethiopia, where wheat, barley, and other Southwest Asian crops have been cultivated for a long time. Ethiopians also domesticated many locally available wild species to obtain crops, most of which are still confined to Ethiopia, but one of them has now spread around the world. However, it is not yet known whether Ethiopians were cultivating these local plants before or only after the arrival of the Southwest Asian package. In these and other areas where food production depended on the arrival of founder crops from elsewhere, did local hunter-gatherers themselves adopt those founder crops from neighboring farming peoples and thereby become farmers themselves? Or was the founder package instead brought by invading farmers, who were thereby enabled to outbreed the local hunters and to kill, displace, or outnumber them? In Egypt, it seems likely that the former happened. Local hunter-gatherers simply added Southwest Asian domesticates and farming and herding techniques to their own diet of wild plants and animals, then gradually phased out the wild foods. That is, what arrived to launch food production in Egypt was foreign crops and animals, not foreign peoples. The same may have been true on the Atlantic coast of Europe, where local hunter-gatherers apparently adopted Southwest Asian sheep and cereals over the course of many centuries. In the Cape of South Africa, the local Khoi hunter-gatherers became herders by acquiring sheep and cows from farther north in Africa. Similarly, Native American hunter-gatherers of the U.S. Southwest gradually became farmers by acquiring Mexican crops. In these four areas, the onset of food production provides little or no evidence for the domestication of local plant or animal species, but also little or no evidence for the replacement of human population. At the opposite extreme are regions in which food production certainly began with an abrupt arrival of foreign people as well as of foreign crops and animals. The reason why we can be certain is that the arrivals took place in modern times and involved literate Europeans, who described in innumerable books what happened. Those areas include California, the Pacific Northwest of North America, the Argentine Pampas, Australia, and Siberia. Until recent centuries, these areas were still occupied by hunter-gatherers, Native Americans in the first three cases and Aboriginal Australians or Native Siberians in the last two. Those hunter-gatherers were killed, infected, driven out, or largely replaced by arriving European farmers and herders who brought their own crops and did not domesticate any local wild species after their arrival. In the Cape of South Africa, the arriving Europeans found not only Khoi hunter-gatherers but also Khoi herders who already possessed only domestic animals, not crops. The result was again the start of farming dependent on crops from elsewhere, a failure to domesticate local species, and a massive modern replacement of human population. Finally, the same pattern of an abrupt start of food production dependent on domesticates from elsewhere, and an abrupt and massive population replacement, seems to have repeated itself in many areas in the prehistoric era. In the absence of written records, the evidence of those prehistoric replacements must be sought in the archaeological record or inferred from linguistic evidence. Duchade not only crops and animals but also pottery. Later chapters will describe the two clearest such examples: the Austronesian expansion from South China into the Philippines and Indonesia, and the Bantu expansion over sub-equatorial Africa. Southeastern Europe and Central Europe present a similar picture of an abrupt onset of food production and of pottery making. This onset too probably involved replacement of Old Greeks and Germans by New Greeks and Germans, just as Old gave way to New in the Philippines, Indonesia, and subequatorial Africa. However, the skeletal differences between the earlier hunter-gatherers and the farmers who replaced them are less marked in Europe than in the Philippines, Indonesia, and subequatorial Africa. Hence the case for population replacement in Europe is less strong or less direct. In short, only a few areas of the world developed food production independently, and they did so at widely differing times. From those nuclear areas, hunter-gatherers of some neighboring areas learned food production, and peoples of other neighboring areas were replaced by invading food producers from the nuclear areas again at widely differing times. Finally, peoples of some areas ecologically suitable for food production neither evolved nor acquired agriculture in prehistoric times at all. They persisted as hunter-gatherers until the modern world finally swept upon them. The peoples of areas with a head start on food production thereby gained a head start on the path leading toward guns, germs, and steel. The result was a long series of collisions between the haves and the have-nots of history. How can we explain these geographic differences in the times and modes of onset of food production? That question, one of the most important problems of prehistory, will be the subject of the next 5 chapters. Chapter 6. To farm or not to farm. Formerly, all people on Earth were hunter-gatherers. Why did any of them adopt food production at all? Given that they must have had some reason, why did they do so around 8500 BC in Mediterranean habitats of the Fertile Crescent, only 3,000 years later in the climatically and structurally similar Mediterranean habitats of southwestern Europe? And never indigenously in the similar Mediterranean habitats of California, southwestern Australia, and the Cape of South Africa? Why did even people of the Fertile Crescent wait until 8500 BC, instead of becoming food producers already around 18,500 or 28,500 BC? From our modern perspective, all these questions at first seem silly, because the drawbacks of being a hunter-gatherer appear so obvious. Scientists used to quote a phrase of Thomas Hobbes's in order to characterize the lifestyle of hunter-gatherers as nasty, brutish, and short. They seem to have to work hard, to be driven by the daily quest for food, often to be close to starvation, to lack such elementary material comforts as soft beds and adequate clothing, and to die young. In reality, only for today's affluent first-world citizens, who don't actually do the work of raising food themselves, does food production mean less physical work, more comfort, freedom from starvation, and a longer expected lifetime. Most peasant farmers and herders, who constitute the great majority of the world's actual food producers, aren't necessarily better off than hunter-gatherers. Time budget studies show that they may spend more rather than fewer hours per day at work than hunter-gatherers do. Archaeologists have demonstrated that the first farmers in many areas were smaller and less well-nourished, suffered from more serious diseases, and died on the average at a younger age than the hunter-gatherers they replaced. If those first farmers could have foreseen the consequences of adopting food production, they might not have opted to do so. Why, unable to foresee the result, did they nevertheless make that choice? To farm or not to farm. There exist many actual cases of hunter-gatherers who did see food production practiced by their neighbors, and who nevertheless refused to accept its supposed blessings and instead remained hunter-gatherers. For instance, Aboriginal hunter-gatherers of northeastern Australia traded for thousands of years with farmers of the Torres Strait Islands, between Australia and New Guinea. California Native American hunter-gatherers traded with Native American farmers in the Colorado River Valley. In addition, Khoi herders west of the Fish River of South Africa traded with Bantu farmers east of the Fish River, and continued to dispense with farming themselves. Why? Still other hunter-gatherers in contact with farmers did eventually become farmers, but only after what may seem to us like an inordinately long delay. For example, the coastal peoples of northern Germany did not adopt food production until 1,300 years after peoples of the linear Ban-Kuramic culture introduced it to inland parts of Germany only 125 miles to the south. Why did those coastal Germans wait so long, and what led them finally to change their minds? Before we can answer these questions, we must dispel some misconceptions about the origins of food production and then reformulate the question. What actually happened was not a discovery of food production, nor an invention, as we might first assume.
There was often not even a conscious choice between food production and hunting-gathering.
Specifically, in each area of the globe, the first people who adopted food production could obviously not have been making a conscious choice or consciously striving toward farming as a goal, because they had never seen farming and had no way of knowing what it would be like. Instead, as we shall see, food production evolved as a byproduct of decisions made without awareness of their consequences. Hence, the question that we have to ask is why food production did evolve, why it evolved in some places but not others, why at different times in different places, and why not instead at some earlier or later date.
Another misconception is that there is necessarily a sharp divide between nomadic hunter-gatherers and sedentary food producers.
In reality, although we frequently draw such a contrast, hunter-gatherers in some productive areas, including North America's Pacific Northwest coast and possibly southeastern Australia, became sedentary but never became food producers. Other hunter-gatherers, in Palestine, coastal Peru, and Japan, became sedentary first and adopted food production much later. Sedentary groups probably made up a much higher fraction of hunter-gatherers 15,000 years ago, when all inhabited parts of the world were still occupied by hunter-gatherers, than they do today, when the few remaining hunter-gatherers survive only in unproductive areas where nomadism is the sole option.
Conversely, there are mobile groups of food producers.
Some modern nomads of New Guinea's Lakes Plains make clearings in the jungle, plant bananas and papayas, go off for a few months to live again as hunter-gatherers, return to check on their crops, weed the garden if they find the crops growing, set off again to hunt, return months later to check again, and settle down for a while to harvest and eat if their garden has produced. Apache Indians of the southwestern United States settled down to farm in the summer at higher elevations and toward the north, then withdrew to the south and to lower elevations to wander in search of wild foods during the winter. Many herding peoples of Africa and Asia shift camp along regular seasonal routes to take advantage of predictable seasonal changes in pasturage. Thus, the shift from hunting-gathering to food production did not always coincide with a shift from nomadism to sedentary living. Another supposed dichotomy that becomes blurred in reality is a distinction between food producers as active managers of their land and hunter-gatherers as mere collectors of the land's wild produce. In reality, some hunter-gatherers intensively manage their land. For example, New Guinea peoples who never domesticated sago palms or mountain pandanus nevertheless increase production of these wild edible plants by clearing away encroaching competing trees, keeping channels in sago swamps clear, and promoting growth of new sago shoots by cutting down mature sago trees. Aboriginal Australians who never reached the stage of farming yams and seed plants nonetheless anticipated several elements of farming. They managed the landscape by burning it, to encourage the growth of edible seed plants that sprout after fires. In gathering wild yams, they cut off most of the edible tuber but replaced the stems and tops of the tubers in the ground so that the tubers would regrow. Their digging to extract the tuber loosened and aerated the soil and fostered regrowth. All that they would have had to do to meet the definition of farmers was to carry the stems and remaining attached tubers home and similarly replace them in soil at their camp. From those precursors of food production already practiced by hunter-gatherers, it developed stepwise. Not all the necessary techniques were developed within a short time, and not all the wild plants and animals that were eventually domesticated in a given area were domesticated simultaneously. Even in the cases of the most rapid independent development of food production from a hunting-gathering lifestyle, it took thousands of years to shift from complete dependence to farm or not to farm on wild foods to a diet with very few wild foods. In early stages of food production, people simultaneously collected wild foods and raised cultivated ones, and diverse types of collecting activities diminished in importance at different times as reliance on crops increased.
The underlying reason why this transition was piecemeal is that food production systems evolved as a result of the accumulation of many separate decisions about allocating time and effort.
Foraging humans, like foraging animals, have only finite time and energy, which they can spend in various ways. We can picture an incipient farmer waking up and asking, "Shall I spend today hoeing my garden, gathering shellfish, or hunting deer, yielding possibly a lot of meat today?"
But more likely nothing?
Human and animal foragers are constantly prioritizing and making effort allocation decisions, even if only unconsciously. They concentrate first on favorite foods, or ones that yield the highest payoff. If these are unavailable, they shift to less and less preferred foods. Many considerations enter into these decisions. People seek food in order to satisfy their hunger and fill their bellies. They also crave specific foods, such as protein-rich foods, fat, salt, sweet fruits, and foods that simply taste good. All other things being equal, people seek to maximize their return of calories, protein, or other specific food categories by foraging in a way that yields the most return with the greatest certainty in the least time for the least effort. Simultaneously, they seek to minimize their risk of starving. Moderate but reliable returns are preferable to a fluctuating lifestyle with a high time-averaged rate of return but a substantial likelihood of starving to death. One suggested function of the first gardens of nearly 11,000 years ago was to provide a reliable reserve larder as insurance in case wild food supplies failed. Conversely, men hunters tend to guide themselves by considerations of prestige. For example, they might rather go giraffe hunting every day, bag a giraffe once a month, and thereby gain the status of great hunter, then bring home twice a giraffe's weight of food in a month by humbling themselves and reliably gathering nuts every day. People are also guided by seemingly arbitrary cultural preferences, such as considering fish either delicacies or taboo. Finally, their priorities are heavily influenced by the relative values they attach to different lifestyles, just as we can see today. For instance, in the 19th century US West, the cattlemen, sheepmen, and farmers all despised each other. Similarly, throughout human history, farmers have tended to despise hunter-gatherers as primitive, hunter-gatherers have despised farmers and ignorant, and herders have despised both. All these elements come into play in people's separate decisions about how to obtain their food. As we already noted, the first farmers on each continent could not have chosen farming consciously, because there were no other nearby farmers for them to observe. However, once food production had arisen in one part of a continent, neighboring hunter-gatherers could see the result and make conscious decisions. In some cases, the hunter-gatherers adopted the neighboring system of food production virtually as a complete package. In others, they chose only certain elements of it, and in still others, they rejected food production entirely and remained hunter-gatherers. For example, hunter-gatherers in parts of southeastern Europe had quickly adopted Southwest Asian cereal crops, pulse crops, and livestock simultaneously as a complete package by around 1600 BCE. All three of these elements also spread rapidly through Central Europe in the centuries before 1500 BCE. Adoption of food production may have been rapid and wholesale in southeastern and Central Europe because the hunter-gatherer lifestyle there was less productive and less competitive. In contrast, food production was adopted piecemeal in southwestern Europe, where sheep arrived first and cereals later. The adoption of intensive food production from the Asian mainland was also very slow and piecemeal in Japan, probably because the hunter-gatherer lifestyle based on seafood and local plants was so productive there. Just as a hunting-gathering lifestyle can be traded piecemeal for a food-producing lifestyle, one system of food production can also be traded piecemeal for another. For example, Indians of the eastern United States were domesticating local plants by about 2500 BC but had trade connections with Mexican Indians who developed a more productive crop system based on the trinity of corn, squash, and beans. Eastern U.S. Indians adopted Mexican crops, and many of them discarded many of their local domesticates. Piecemeal, squash was domesticated independently, corn arrived from Mexico around AD 200 but remained a minor crop until around AD 900. And beans arrived a century or two later. It even happened that food production systems were abandoned in favor of hunting-gathering. For instance, around 300 BC the hunter-gatherers of southern Sweden adopted farming based on Southwest Asian crops, but abandoned it around 2700 BC and reverted to hunting-gathering for 400 years before resuming farming. All these considerations make it clear that we should not suppose that the decision to adopt farming was made in a vacuum, as if the people had previously to farm or not to farm, had no means to feed themselves. Instead, we must consider food production and hunting-gathering as alternative strategies competing with each other. Mixed economies that added certain crops or livestock to hunting-gathering also competed against both types of pure economies, and against mixed economies with higher or lower proportions of food production. Nevertheless, over the last 10,000 years, the predominant result has been a shift from hunting-gathering to food production. Hence we must ask, what were the factors that tipped the competitive advantage away from the former and toward the latter? That question continues to be debated by archaeologists and anthropologists. One reason for its remaining unsettled is that different factors may have been decisive in different parts of the world. Another has been the problem of disentangling cause and effect in the rise of food production. However, 5 main contributing factors can still be identified. The controversies revolve mainly around their relative importance. One factor is the decline in the availability of wild foods. The lifestyle of hunter-gatherers has become increasingly less rewarding over the past 13,000 years, as resources on which they depended have become less abundant or even disappeared. As we saw in Chapter 1, most large mammal species became extinct in North and South America at the end of the Pleistocene, and some became extinct in Eurasia and Africa, either because of climate changes or because of the rise in skill and numbers of human hunters. While the role of animal extinctions in eventually nudging ancient Native Americans, Eurasians, and Africans toward food production can be debated, there are numerous incontrovertible cases on islands in more recent times. Only after the first Polynesian settlers had exterminated moas and decimated seal populations on New Zealand, and exterminated or decimated seabirds and landbirds on other Polynesian islands, did they intensify their food production. For instance, although the Polynesians who colonized Easter Island around AD 500 brought chickens with them, chicken did not become a major food until wild birds and porpoises were no longer readily available as food. Similarly, a suggested contributing factor to the rise of animal domestication in the Fertile Crescent was the decline in abundance of the wild gazelles that had previously been a major source of meat for hunter-gatherers in that area. A second factor is that, just as the depletion of wild game tended to make hunting-gathering less rewarding, an increased availability of domesticable wild plants made steps leading to plant domestication more rewarding. For instance, climate changes at the end of the Pleistocene in the Fertile Crescent greatly expanded the area of habitats with wild cereals, of which huge crops could be harvested in a short time. Those wild cereal harvests were precursors to the domestication of the earliest crops, the cereals wheat and barley, in the Fertile Crescent. Still another factor tipping the balance away from hunting-gathering was the cumulative development of technologies on which food production would eventually depend: technologies for collecting, processing, and storing wild foods. What use can would-be farmers make of a ton of wheat grains on the stalk, if they have not first figured out how to harvest, husk, and store them? The necessary methods, implements, and facilities appeared rapidly in the Fertile Crescent after 11,000 BC. Having been invented for dealing with newly available abundance of wild cereals. Those inventions included sickles of flint blades cemented into wooden or bone handles, for harvesting wild grains, baskets in which to carry the grains home from the hillsides where they grew, mortars and pestles, or grinding slabs, to remove the husks, the technique of roasting grains so that they could be stored without sprouting. And underground storage pits, some of them plastered to make them waterproof. Evidence for all of these techniques becomes abundant at sites of hunter-gatherers in the Fertile Crescent after 11,000 BC. All these techniques, though developed for the exploitation of wild cereals, were prerequisites to the planting of cereals as crops. These cumulative developments constituted the unconscious first steps of plant domestication. A fourth factor was the two-way link between the rise in human population density and the rise in food production. In all parts of the world where adequate evidence is available, archaeologists find evidence of rising densities associated with the appearance of food production. Which was the cause and which the result? This is a long-debated chicken or egg problem. Did a rise in human population density force people to turn to food production, or did food production permit a rise in human population density? In principle, one expects the chain of causation to operate in both directions. As I've already discussed, food production tends to lead to increased population densities because it yields more edible calories per acre than does hunting-gathering. On the other hand, human population densities were gradually rising throughout the late Pleistocene anyway,
thanks to improvements in human technology for collecting and processing wild foods. As population densities rose, food production became increasingly favored because it provided the increased food outputs needed to feed all those people. That is, the adoption of food production exemplifies what is termed an autocatalytic process, one that catalyzes itself in a positive feedback cycle, going faster. To farm or not to farm. And faster once it has started. A gradual rise in population densities impelled people to obtain more food, by rewarding those who unconsciously took steps toward producing it. Once people began to produce food and become sedentary, they could shorten the birth spacing and produce still more people, requiring still more food. This bidirectional link between food production and population density explains the paradox that food production, while increasing the quantity of edible calories per acre, left the food producers less well nourished than the hunter-gatherers whom they succeeded. That paradox developed because human population densities rose slightly more steeply than did the availability of food. Taken together, these four factors help us understand why the transition to food production in the Fertile Crescent began around 8500 BC, not around 18,500 or 28,500 BC. At the latter two dates, hunting-gathering was still much more rewarding than incipient food production, because wild mammals were still abundant, wild cereals were not yet abundant, people had not yet developed the inventions necessary for collecting, processing, and storing cereals efficiently. And human population densities were not yet high enough for a large premium to be placed on extracting more calories per acre. A final factor in the transition became decisive at geographic boundaries between hunter-gatherers and food producers. The much denser populations of food producers enabled them to displace or kill hunter-gatherers by their sheer numbers, not to mention the other advantages associated with food production. In areas where there were only hunter-gatherers to begin with, those groups of hunter-gatherers who adopted food production outbred those who didn't. As a result, in most areas of the globe suitable for food production, hunter-gatherers met one of two fates: either they were displaced by neighboring food producers, or else they survived only by adopting food production themselves. In places where they were already numerous or where geography retarded immigration by food producers, local hunter-gatherers did have time to adopt farming in prehistoric times and thus to survive as farmers. This may have happened in the U.S. Southwest, in the western Mediterranean, on the Atlantic coast of Europe, and in parts of Japan. However, in Indonesia, tropical Southeast Asia, most of subequatorial Africa, and probably in parts of Europe, the hunter-gatherers were replaced by farmers in the prehistoric era, whereas a similar replacement took place in modern times in Australia and much of the western United States. To farm or not to farm. Makes very difficult were hunter-gatherers able to persist until modern times in areas suitable for food production. The three outstanding examples are the persistence of Native American hunter-gatherers in California, separated by deserts from the Native American farmers of Arizona, that of Khoisan hunter-gatherers at the Cape of South Africa. In a Mediterranean climate zone unsuitable for the equatorial crops of nearby Bantu farmers, and that of hunter-gatherers throughout the Australian continent, separated by narrow seas from the food producers of Indonesia and New Guinea. Those few peoples who remained hunter-gatherers into the 20th century escaped replacement by food producers because they were confined to areas not fit for food production, especially deserts and Arctic regions. Within the present decade, even they will have been seduced by the attractions of civilization, settled down under pressure from bureaucrats or missionaries, or succumbed to germs. Chapter 7. How to make an almond. If you're a hiker whose appetite is jaded by farm-grown foods, it's fun to try eating wild foods. You know that some wild plants, such as wild strawberries and blueberries, are both tasty and safe to eat. They're sufficiently similar to familiar crops that you can easily recognize the wild berries, even though they're much smaller than those we grow. Adventurous hikers cautiously eat mushrooms, aware that many species can kill us. But not even ardent nut lovers eat wild almonds, of which a few dozen contain enough cyanide to kill us. The forest is full of many other plants deemed inedible, yet all crops arose from wild plant species. How did certain wild plants get turned into crops? That question is especially puzzling in regard to the many crops whose wild progenitors are lethal or bad tasting, and to other crops that look drastically different from their wild ancestors. What cave woman or caveman ever got the idea of domesticating a plant, and how was it accomplished?
Plant domestication may be defined as growing a plant and thereby, consciously or unconsciously, causing it to change genetically from its wild ancestor in ways making it more useful to human consumers.
Crop development is today a conscious, highly specialized effort carried out by professional scientists.
They already know about the hundreds of existing crops and set out to develop yet another one. To achieve this goal, they plant many different seeds or roots, select the best progeny and plant their seeds, apply knowledge of genetics to develop good varieties that breed true, and perhaps even use the latest techniques of genetic engineering to transfer specific useful genes. At the Davis campus of the University of California, an entire department is devoted to apples and another to grapes and wine. But plant domestication goes back over 10,000 years. Early farmers surely didn't use molecular genetic techniques to arrive at their results. The first farmers didn't even have any existing crop as a model to inspire them to develop new ones. Hence they couldn't have known that, whatever they were doing, they would enjoy a tasty treat as a result.
How, then, did early farmers domesticate plants unwittingly? For example, how did they turn poisonous almonds into safe ones without knowing what they were doing? What changes did they actually make in wild plants, besides rendering some of them bigger or less poisonous? Even for valuable crops. The times of domestication vary greatly. For instance, peas were domesticated by 800 BC, olives around 400 BC, strawberries not until the Middle Ages, and pecans not until 1846.
Many valuable wild plants yielding food prized by millions of people, such as oaks sought for their edible acorns in many parts of the world, remain untamed even today.
What made some plants so much easier or more inviting to domesticate than others?
Why did olive trees yield to Stone Age farmers, whereas oak trees continue to defeat our brightest agronomists?
Let's begin by looking at domestication from the plant's point of view.
As far as plants are concerned, we're just one of thousands of animal species that unconsciously domesticate plants. Like all animal species, plants must spread their offspring to areas where they can thrive and pass on their parents' genes.
Young animals disperse by walking or flying, but plants don't have that option, so they must somehow hitchhike.
While some plant species have seeds adapted for being carried by the wind or for floating on water, many others trick an animal into carrying their seeds by wrapping the seed in a tasty fruit and advertising the fruit's ripeness by its color or smell. The hungry animal plucks and swallows the fruit, walks or flies off, and then spits out or defecates the seed somewhere far from its parent tree. Seeds can in this manner be carried for thousands of miles. It may come as a surprise to learn that plant seeds can resist digestion by your gut and nonetheless germinate out of your feces. But any adventurous readers who are not too squeamish can make the test and prove it for themselves.
The seeds of many wild plant species actually must pass through an animal's gut before they can germinate.
For instance, one African melon species is so well adapted to being eaten by a hyena-like animal called the aardwolf that most melons of that species grow on the latrine sites of aardwolves.
As an example of how would-be plant hitchhikers attract animals, consider 90. How to make an almond.
Wild strawberries. When strawberry seeds are still young and not yet ready to be planted, the surrounding fruit is green, sour, and hard.
When the seeds finally mature, the berries turn red, sweet, and tender.
The change in the berry's color serves as a signal attracting birds like thrushes to pluck the berries and fly off, eventually to spit out or defecate the seeds. Naturally, strawberry plants didn't set out with a conscious intent of attracting birds when, and only when, their seeds were ready to be dispersed.
Neither did thrushes set out with the intent of domesticating strawberries. Instead, strawberry plants evolved through natural selection.
The greener and more sour the young strawberry, the fewer the birds that destroyed the seeds by eating berries before the seeds were ready, the sweeter and redder the final strawberry, the more numerous the birds that dispersed its ripe seeds. Countless other plants have fruits adapted to being eaten and dispersed by particular species of animals. Just as strawberries are adapted to birds, so acorns are adapted to squirrels, mangoes to bats, and some sedges to ants. That fulfills part of our definition of plant domestication, as the genetic modification of an ancestral plant in ways that make it more useful to consumers. But no one would seriously describe this evolutionary process as domestication, because birds and bats and other animal consumers don't fulfill the other part of the definition. They don't consciously grow plants. In the same way, the early unconscious stages of crop evolution from wild plants consisted of plants evolving in ways that attracted humans to eat and disperse their fruit without yet intentionally growing them. Human latrines, like those of aardwolves, may have been a testing ground of the first unconscious crop breeders. Latrines are merely one of the many places where we accidentally sow the seeds of wild plants that we eat. When we gather edible wild plants and bring them home, some spill en route or at our houses. Some fruit rots while still containing perfectly good seeds, and gets thrown out uneaten into the garbage. As parts of the fruit that we actually take into our mouths, strawberry seeds are tiny and inevitably swallowed and defecated, but other seeds are large enough to be spat out. Thus, our spittoons and garbage dumps joined our latrines to form the first agricultural research laboratories. At whichever such lab the seeds ended up, they tended to come from only certain individuals of edible plants, namely, those that we preferred to eat for one reason or another. From your berry picking days, you know that you select particular berries or berry bushes. Eventually, when the first farmers began to sow seeds deliberately, they would inevitably sow those from the plants they had chosen to gather, even though they didn't understand the genetic principle that big berries have seeds likely to grow into bushes yielding more big berries. So, when you wade into a thorny thicket amid the mosquitoes on a hot, humid day, you don't do it for just any strawberry bush. Even if unconsciously, you decide which bush looks most promising, and whether it's worth it at all. What are your unconscious criteria? One criterion, of course, is size. You prefer large berries, because it's not worth your while to get sunburned and mosquito bitten for some lousy little berries. That provides part of the explanation why many crop plants have much bigger fruits than their wild ancestors do. It's especially familiar to us that supermarket strawberries and blueberries are gigantic compared with wild ones. Those differences arose only in recent centuries. Such size differences in other plants go back to the very beginnings of agriculture, when cultivated peas evolved through human selection to be 10 times heavier than wild peas. The little wild peas had been collected by hunter-gatherers for thousands of years, just as we collect little wild blueberries today, before the preferential harvesting and planting of the most appealing largest wild peas, that is. What we call farming began automatically to contribute to increases in average pea size from generation to generation. Similarly, supermarket apples are typically around 3 inches in diameter, wild apples only 1 inch. The oldest corn cobs are barely more than half an inch long, but Mexican Indian farmers of AD 1500 already had developed 6-inch cobs, and some modern cobs are 1.5 feet long. Another obvious difference between seeds that we grow and many of their wild ancestors is in bitterness. Many wild seeds evolved to be bitter, bad-tasting, or actually poisonous, in order to deter animals from eating them. Thus, natural selection acts oppositely on seeds and on fruits. Plants whose fruits are tasty get their seeds dispersed by animals, but the seed itself within the fruit has to be bad-tasting. Otherwise, the animal would also chew up the seed, and it couldn't sprout. Almonds provide a striking example of bitter seeds and their change under domestication. Most wild almond seeds contain an intensely bitter chemical called amygdalin, which breaks down to yield the poison cyanide. A snack of wild almonds can kill a person foolish enough to ignore the warning of the bitter taste. Since the first stage in unconscious domestication involves gathering seeds to eat, how on earth did domestication of wild almonds ever? How to make an almond? Reach that first stage? The explanation is that occasional individual almond trees have a mutation in a single gene that prevents them from synthesizing the bitter-tasting amygdalin. Such trees die out in the wild without leaving any progeny, because birds discover and eat all their seeds. But curious or hungry children of early farmers, nibbling wild plants around them, would eventually have sampled and noticed those non-bitter almond trees. Those non-bitter almond seeds are the only ones that ancient farmers would have planted, at first unintentionally in their garbage heaps and later intentionally in their orchards. Already by 800 BC wild almonds show up in excavated archaeological sites in Greece.
By 3000 BC, they were being domesticated in lands of the eastern Mediterranean. When the Egyptian king Tutankhamun died, around 1325 BC, almonds were one of the foods left in his famous tomb to nourish him in the afterlife. Lima beans, watermelons, potatoes, eggplants, and cabbages are among the many other familiar crops whose wild ancestors were bitter or poisonous, and of which occasional sweet individuals must have sprouted around the latrines of ancient hikers. While size and tastiness are the most obvious criteria by which human hunter-gatherers select wild plants, other criteria include fleshy or seedless fruits, oily seeds, and long fibers. Wild squashes and pumpkins have little or no fruit around their seeds, but the preferences of early farmers selected for squashes and pumpkins consisting of far more flesh than seeds. Cultivated bananas were selected long ago to be all flesh and no seed, thereby inspiring modern agricultural scientists to develop seedless oranges, grapes, and watermelons as well. Seedlessness provides a good example of how human selection can completely reverse the original evolved function of a wild fruit, which in nature serves as a vehicle for dispersing seeds. In ancient times, many plants were similarly selected for oily fruits or seeds. Among the earliest fruit trees domesticated in the Mediterranean world were olives, cultivated since around 4000 BC for their oil. Crop olives are not only bigger but also oilier than wild ones. Ancient farmers selected sesame, mustard, poppies, and flax as well for oily seeds, while modern plant scientists have done the same for sunflower, safflower, and cotton. Before that recent development of cotton for oil, it was of course selected for its fibers, used to weave textiles. The fibers are hairs on the cotton seeds, and early farmers of both the Americas and the Old World independently selected different species of cotton for long lint. In flax and hemp, two other plants grown to supply the textiles of antiquity, the fibers come instead from the stem, and plants were selected for long, straight stems. While we think of most crops as being grown for food, flax is one of our oldest crops. It furnished linen, which remained the chief textile of Europe until it became supplanted by cotton and synthetics after the Industrial Revolution. So far, all the changes that I've described in the evolution of wild plants into crops involve characters that early farmers could actually notice, such as fruit size, bitterness, fleshiness, and oiliness, and fiber length. By harvesting those individual wild plants possessing these desirable qualities to an exceptional degree, ancient peoples unconsciously dispersed the plants and set them on the road to domestication. In addition, though, there were at least 4 other major types of change that did not involve berry pickers making visible choices. In these cases, the berry pickers caused changes either by harvesting available plants while other plants remained unavailable for invisible reasons, or by changing the selective conditions acting on plants. The first such change affected wild mechanisms for the dispersal of seeds. Many plants have specialized mechanisms that scatter seeds. Only mutant seeds lacking those mechanisms would have been harvested and would thus have become the progenitors of crops. A clear example involves peas, whose seeds come enclosed in a pod. Wild peas have to get out of the pod if they are to germinate. To achieve that result, pea plants evolved a gene that makes the pod explode, shooting out the peas onto the ground. Pods of occasional mutant peas don't explode. In the wild, the mutant peas would die entombed in their pod on their parent plants, and only the popping pods would pass on their genes. But, conversely, the only pods available to humans to harvest would be the non-popping ones left on the plant. Thus, once humans began bringing wild peas home to eat, there was immediate selection for that single gene mutant. Similar non-popping mutants were selected in lentils, flax, and poppies. Instead of being enclosed in a poppyable pod, wild wheat and barley seeds grow at the top of a stalk that spontaneously shatters, dropping the seeds to the ground where they can germinate. A single gene mutation prevents the stalks from shattering. In the wild, that mutation would be lethal to the plant, since the How to make an almond. Seeds would remain suspended in the air, unable to germinate and take root. But those mutant seeds would have been the ones waiting conveniently on the stalk to be harvested and brought home by humans. When humans then planted those harvested mutant seeds, any mutant seeds among the progeny again became available to the farmers to harvest, and so,
while normal seeds among the progeny fell to the ground and became unavailable. Thus, human farmers reversed the direction of natural selection by 180 degrees. The formerly successful gene suddenly became lethal, and the lethal mutant became successful. Over 10,000 years ago, that unconscious selection for non-shattering wheat and barley stalks was apparently the first major human improvement in any plant. That change marked the beginning of agriculture in the Fertile Crescent. The second type of change was even less visible to ancient hikers. For annual plants growing in an area with a very unpredictable climate, it could be lethal if all the seeds sprouted quickly and simultaneously. Were that to happen, the seedlings might all be killed by a single drought or frost, leaving no seeds to propagate the species. Hence, many annual plants have evolved to hedge their bets by means of germination inhibitors, which make seeds initially dormant and spread out their germination over several years. In that way, even if most seedlings are killed by a bout of bad weather, some seeds will be left to germinate later. A common bet hedging adaptation by which wild plants achieve that result is to enclose their seeds in a thick coat or armor. The many wild plants with such adaptations include wheat, barley, peas, flax, and sunflowers. While such late sprouting seeds still have the opportunity to germinate in the wild, consider what must have happened as farming developed. Early farmers would have discovered by trial and error that they could obtain higher yields by tilling and watering the soil and then sowing seeds. When that happened, seeds that immediately sprouted grew into plants whose seeds were harvested and planted in the next year. But many of the wild seeds did not immediately sprout, and they yielded no harvest. Occasional mutant individuals among wild plants lacked thick seed coats or other inhibitors of germination. All such mutants promptly sprouted and yielded harvest mutant seeds. Early farmers wouldn't have noticed the difference, in the way that they did notice and selectively harvest big berries. But the cycle of sow-grow-harvest-sow would have selected immediately and unconsciously for the mutants. Like the changes in seed dispersal, these changes in germination inhibition characterize wheat, barley, peas, and many other crops compared with their wild ancestors. The remaining major type of change invisible to early farmers involved plant 95. Reproduction. A general problem in crop development is that occasional mutant plant individuals are more useful to humans than are normal individuals. If those desirable mutants proceeded to interbreed with normal plants, the mutation would immediately be diluted or lost. Under what circumstances would it remain preserved for early farmers? For plants that reproduce themselves, the mutant would automatically be preserved. That's true of plants that reproduce vegetatively, or that are hermaphrodites capable of fertilizing themselves. But the vast majority of wild plants don't reproduce that way. They're either hermaphrodites incapable of fertilizing themselves and forced to interbreed with other hermaphrodite individuals, or else they occur as separate male and female individuals, like all normal mammals. The former plants are termed self-incompatible hermaphrodites, the latter, dioecious species. Both were bad news for ancient farmers, who would thereby have promptly lost any favorable mutants without understanding why. The solution involved another type of invisible change. Numerous plant mutations affect the reproductive system itself. Some mutant individuals developed fruit without even having to be pollinated, resulting in our seedless bananas, grapes, oranges, and pineapples. Some mutant hermaphrodites lost their self-incompatibility and became able to fertilize themselves, a process exemplified by many fruit trees such as plums, peaches, apples, apricots, and cherries. Some mutant grapes that normally would have had separate male and female individuals also became self-fertilizing hermaphrodites. By all these means, ancient farmers, who didn't understand plant reproductive biology, still ended up with useful crops that bred true and were worth replanting, instead of initially promising mutants whose worthless progeny were consigned to oblivion. Thus, farmers selected from among individual plants on the basis not only of perceptible qualities like size and taste, but also of invisible features like seed dispersal mechanisms, germination inhibition, and reproductive biology. As a result, different plants became selected for quite different or even opposite features. Some plants were selected for much bigger seeds, while others were selected for tiny or even non-existent seeds. Lettuce was selected for luxuriant leaves at the expense of seeds or fruit, wheat and sunflowers for seeds at the expense of leaves, and squash for fruit at the expense of leaves. Especially instructive are cases in which a single wild plant species was variously selected for different purposes and thereby gave rise to quite different looking crops.
Beets. How to make an almond.
Grown already in Babylonian times for their leaves, were then developed for their edible roots and finally for their sugar content. Ancestral cabbage plants, possibly grown originally for their oily seeds, underwent even greater diversification as they became variously selected for leaves, stems, buds, or flower shoots. So far, we have been discussing transformations of wild plants into crops as a result of selection by farmers, consciously or unconsciously. That is, farmers initially selected seeds of certain wild plant individuals to bring into their gardens and then chose certain progeny seeds each year to grow in the next year's garden. But much of the transformation was also affected as a result of plants selecting themselves. Darwin's phrase natural selection refers to certain individuals of a species surviving better and/or reproducing more successfully than competing individuals of the same species under natural conditions.
In effect, the natural processes of differential survival and reproduction do the selecting.
If the conditions change, different types of individuals may now survive or reproduce better and become naturally selected, with the result that the population undergoes evolutionary change. A classic example is the development of industrial melanism in British moths. Darker moth individuals became relatively commoner than paler individuals as the environment became dirtier during the 19th century, because dark moths resting on a dark, dirty tree were more likely than contrasting pale moths to escape the attention of predators.
Much as the Industrial Revolution changed the environment for moths, farming changed the environment for plants.
A tilled, fertilized, watered, weeded garden provides growing conditions very different from those on a dry, unfertilized hillside. Many changes of plants under domestication resulted from such changes in conditions and hence in the favored types of individuals. For example, when a farmer sows seeds densely in a garden, there is intense competition among the seeds.
Big seeds that can take advantage of the good conditions to grow quickly will now be favored over small seeds that were previously favored on dry, unfertilized hillsides where seeds were sparser and competition less intense.
Such increased competition among plants themselves made a major contribution to larger seed size and to many other changes developing during the transformation of wild plants into ancient crops.
What accounts for the great differences among plants in ease of domestication, such that some species were domesticated long ago and others not until the Middle Ages, whereas still other wild plants have proved immune to all our activities?
We can deduce many of the answers by examining the well-established sequence in which various crops developed in Southwest Asia's Fertile Crescent. It turns out that the earliest Fertile Crescent crops, such as the wheat and barley and peas domesticated around 10,000 years ago, arose from wild ancestors offering many advantages. They were already edible and gave high yields in the wild. They were easily grown, merely by being sown or planted. They grew quickly and could be harvested within a few months of sowing, a big advantage for incipient farmers still on the borderline between nomadic hunters and settled villagers. They could be readily stored, unlike many later crops such as strawberries and lettuce. They were mostly self-pollinating, that is, the crop varieties could pollinate themselves and pass on their own desirable genes unchanged, instead of having to hybridize with other varieties less useful to humans. Finally, their wild ancestors required very little genetic change to be converted into crops. For instance, in wheat, just the mutations for non-shattering stalks and uniform quick germination. A next stage of crop development included the first fruit and nut trees, domesticated around 1400 BC. They comprised olives, figs, dates, pomegranates, and grapes. Compared with cereals and legumes, they had the drawback of not starting to yield food until at least 3 years after planting, and not reaching full production until after as much as a decade. Thus, growing these crops was possible only for people already fully committed to the settled village life. However, these early fruit and nut trees were still the easiest such crops to cultivate. Unlike later tree domesticates, they could be grown directly by being planted as cuttings or even seeds. Cuttings have the advantage that, once ancient farmers had found or developed a productive tree, they could be sure that all its descendants would remain identical to it. A third stage involved fruit trees that proved much harder to cultivate, including apples, pears, plums, and cherries. These trees cannot be grown from cuttings. It's also a waste of effort to grow them from seed, since the offspring even of an outstanding individual tree of those species are highly variable and mostly yield worthless fruit. Instead, those trees must be grown by the difficult technique of grafting, developed in China long after the beginnings of agriculture. Not only is grafting hard work even once you know the principle, but the principle itself could have been discovered only through conscious experimentation. The invention of grafting was hardly just a matter of some nomad relieving herself at a latrine and returning later to be pleasantly surprised by the resulting crop of fine fruit. Many of these late-stage fruit trees posed a further problem in that they're wild.
How to make an almond. Progenitors were the opposite of self-pollinating.
They had to be cross-pollinated by another plant belonging to a genetically different variety of their species. Hence early farmers either had to find mutant trees not requiring cross-pollination, or had consciously to plant genetically different varieties or else male and female individuals nearby in the same orchard. All those problems delayed the domestication of apples, pears, plums, and cherries until around classical times. At about the same time, though, another group of late domesticates arose with much less effort, as wild plants that established themselves initially as weeds in fields of intentionally cultivated crops.
Crops starting out as weeds included rye and oats, turnips and radishes, beets and leeks, and lettuce.
Although the detailed sequence that I've just described applies to the Fertile Crescent, partly similar sequences also appeared elsewhere in the world. In particular, the Fertile Crescent's wheat and barley exemplify the class of crops termed cereals or grains, while Fertile Crescent peas and lentils exemplify pulses. Cereal crops have the virtues of being fast-growing, high in carbohydrates, and yielding up to a ton of edible food per hectare cultivated. As a result, cereals today account for over half of all calories consumed by humans and include 5 of the modern world's 12 leading crops. Many cereal crops are low in protein, but that deficit is made up by pulses, which are often 25% protein. Cereals and pulses together thus provide many of the ingredients of a balanced diet.
As Table 7.1 summarizes, the domestication of local cereal pulse combinations launched food production in many areas.
The most familiar examples are the combination of wheat and barley with peas and lentils in the Fertile Crescent, the combination of corn with several bean species in Mesoamerica, and the combination of rice and millets with soybeans and other beans in China. Less well known are Africa's combination of sorghum, African rice, and pearl millet with cowpeas and groundnuts, and the Andes combination of the non-cereal grain quinoa with several bean species.
Table 7.1 also shows that the Fertile Crescent's early domestication of flax for fiber was paralleled elsewhere.
Hemp, for cotton species, yucca, and agave variously furnished fiber for rope and woven clothing in China, Mesoamerica, India, Ethiopia, Sub-Saharan Africa, and South America, supplemented in several of those areas by wool from domestic animals. Of the centers of early food production, only the eastern United States and New Guinea remained without a fiber crop. Table 7.1 Examples of early major crop types around the ancient world.
Jerusalem artichoke, squash, New Guinea sugar cane, yams, taro.
The table gives major crops of 5 crop classes from early agricultural sites in various parts of the world.
Square brackets enclose names of crops first domesticated elsewhere. Names not enclosed in brackets refer to local domesticates.
Omitted are crops that arrived or became important only later, such as bananas in Africa, corn and beans in the eastern United States, and sweet potato in New Guinea. Cottons are 4 species of the genus Gossypium, each species being native to a particular part of the world. Squashes are 5 species of the genus Cucurbita. Note that cereals, pulses, and fiber crops launched agriculture in most areas, but that root and tuber crops and melons were of early importance in only some areas.
How to make an almond.
Alongside these parallels, there were also some major differences in food production systems around the world. One is that agriculture in much of the Old World came to involve broadcast seeding and monoculture fields, and eventually plowing. That is, seeds were sown by being thrown in handfuls, resulting in a whole field devoted to a single crop. Once cows, horses, and other large mammals were domesticated, they were hitched to plows, and fields were tilled by animal power. In the New World, however, no animal was ever domesticated that could be hitched to a plow. Instead, fields were always tilled by handheld sticks or hoes, and seeds were planted individually by hand and not scattered as whole handfuls. Most New World fields thus came to be mixed gardens of many crops planted together, rather than monoculture. Another major difference among agricultural systems involved the main sources of calories and carbohydrates. As we have seen, these were cereals in many areas. In other areas, though, that role of cereals was taken over or shared by roots and tubers, which were of negligible importance in the ancient Fertile Crescent and China. Manioc and sweet potato became staples in tropical South America, potato and osier in the Andes, African yams in Africa, and Indo-Pacific yams and taro in Southeast Asia and New Guinea. Tree crops, notably bananas and breadfruit, also furnished carbohydrate-rich staples in Southeast Asia and New Guinea. Thus, by Roman times, almost all of today's leading crops were being cultivated somewhere in the world. Just as we shall see for domestic animals too, ancient hunter-gatherers were intimately familiar with local wild plants, and ancient farmers evidently discovered and domesticated almost all of those worth domesticating. Of course, medieval monks did begin to cultivate strawberries and raspberries, and modern plant breeders are still improving ancient crops and have added new minor crops, notably some berries and nuts. But these few modern additions have remained of modest importance compared with ancient staples like wheat, corn, and rice. Still, our list of triumphs lacks many wild plants that, despite their value as food, we never succeeded in domesticating. Notable among these failures of ours are oak trees, whose acorns were a staple food of Native Americans in California and the eastern United States, as well as a fallback food for European peasants in famine times of crop failure. Acorns are nutritionally valuable, being rich in starch and oil. Like many otherwise edible wild foods, most acorns do contain bitter tannins, but acorn lovers learned to deal with tannins in the same way that they dealt with bitter chemicals in almonds and other wild plants, either by grinding and leaching the acorns to remove the tannins, or by harvesting acorns from the occasional mutant individual oak tree low in tannins. Why have we failed to domesticate such a prized food source as acorns? Why did we take so long to domesticate strawberry and raspberries? What is it about those plants that kept their domestication beyond the reach of ancient farmers capable of mastering such difficult techniques as grafting? It turns out that oak trees have 3 strikes against them. First, their slow growth would exhaust the patience of most farmers. Sown wheat yields a crop within a few months, a planted almond grows into a nut-bearing tree in 3 or 4 years, but a planted acorn may not become productive for a decade or more. Second, oak trees evolved to make nuts of a size and taste suitable for squirrels, which we've all seen burying, digging up, and eating acorns. Oaks grow from the occasional acorn that a squirrel forgets to dig up. With billions of squirrels each spreading hundreds of acorns every year to virtually any spot suitable for oak trees to grow, we humans didn't stand a chance of selecting oaks for the acorns that we wanted. Those same problems of slow growth and fast squirrels probably also explain why beech and hickory trees, heavily exploited as wild trees for their nuts by Europeans and Native Americans, respectively, were also not domesticated. Finally, perhaps the most important difference between almonds and acorns is that bitterness is controlled by a single dominant gene in almonds but appears to be controlled by many genes in oaks. If ancient farmers planted almonds or acorns from the occasional non-bitter mutant tree, the laws of genetics dictate that half of the nuts from the resulting tree growing up would also be non-bitter in the case of almonds, but almost all would still be bitter in the case of oaks. That alone would kill the enthusiasm of any would-be acorn farmer who had defeated the squirrels and remained patient. As for strawberries and raspberries, we had similar trouble competing with thrushes and other berry-loving birds. Yes, the Romans did tend wild strawberries in their gardens. But with billions of European thrushes defecating wild strawberry seeds in every possible place, strawberries remained the little berries that thrushes wanted, not the big berries that humans wanted. Only with the recent development of protective nets and greenhouses were we finally able to defeat the thrushes and to redesign strawberries and raspberries according to our own standards.
How to make an almond.
We've thus seen that the difference between gigantic supermarket strawberries and tiny wild ones is just one example of the various features distinguishing cultivated plants from their wild ancestors. Those differences arose initially from natural variation among the wild plants themselves. Some of it, such as the variation in berry size or in nut bitterness, would have been readily noticed by ancient farmers.
Other variation, such as that in seed dispersal mechanisms or seed dormancy, would have gone unrecognized by humans before the rise of modern botany.
But whether or not the selection of wild edible plants by ancient hikers relied on conscious or unconscious criteria, the resulting evolution of wild plants into crops was at first an unconscious process. It followed inevitably from our selecting among wild plant individuals, and from competition among plant individuals in gardens favoring individuals different from those favored in the wild. That's why Darwin, in his great book on the origin of species, didn't start with an account of natural selection. His first chapter is instead a lengthy account of how our domesticated plants and animals arose through artificial selection by humans. Rather than discussing the Galapagos Island birds that we usually associate with him, Darwin began by discussing how farmers develop varieties of gooseberries. He wrote, "I have seen great surprise expressed in horticultural works at the wonderful skill of gardeners in having produced such splendid results from such poor materials, but the art has been simple, and as far as the final result is concerned, has been followed almost unconsciously. It has consisted in always cultivating the best-known variety, sowing its seeds, and, when a slightly better variety chanced to appear, selecting it, and so onwards. Those principles of crop development by artificial selection still serve as our most understandable model of the origin of species by natural selection."
Chapter 8. Apples or Indians.
We have just seen how peoples of some regions began to cultivate wild plant species, a step with momentous unforeseen consequences for their lifestyle and their descendants' place in history. Let us now return to our questions. Why did agriculture never arise independently in some fertile and highly suitable areas, such as California, Europe, temperate Australia, and sub-equatorial Africa? Why, among the areas where agriculture did arise independently,
did it develop much earlier in some than in others?
Two contrasting explanations suggest themselves: problems with the local people or problems with the locally available wild plants. On the one hand, perhaps almost any well-watered temperate or tropical area of the globe offers enough species of wild plants suitable for domestication. In that case, the explanation for agriculture's failure to develop in some of those areas would lie with cultural characteristics of their peoples. On the other hand, perhaps at least some humans in any large area of the globe would have been receptive to the experimentation that led to domestication. Only the lack of suitable wild plants might then explain why food production did not evolve in some areas. As we shall see in the next chapter, the corresponding problem for domestication of big wild mammals proves easier to solve, because there are many fewer species of them than of plants. The world holds only about 148 species of large wild mammalian terrestrial herbivores or omnivores, the large mammals that could be considered candidates for domestication. Only a modest number of factors determines whether a mammal is suitable for domestication.
It's thus straightforward to review a region's big mammals and to test whether the lack of mammal domestication in some regions was due to the unavailability of suitable wild species, rather than to local peoples.
That approach would be much more difficult to apply to plants because of the 104
apples or Indians.
Sheer number 200,000 of species of wild flowering plants, the plants that dominate vegetation on the land and that have furnished almost all of our crops.
We can't possibly hope to examine all the wild plant species of even a circumscribed area like California, and to assess how many of them would have been domesticable. But we shall now see how to get around that problem. When one hears that there are so many species of flowering plants, one's first reaction might be as follows: surely, with all those wild plant species on Earth, any area with a sufficiently benign climate must have had more than enough species to provide plenty of candidates for crop development.
But then reflect that the vast majority of wild plants are unsuitable for obvious reasons. They are woody, they produce no edible fruit, and their leaves and roots are also inedible. Of the 200,000 wild plant species, only a few thousand are eaten by humans, and just a few hundred of these have been more or less domesticated. Even of these several hundred crops, most provide minor supplements to our diet and would not by themselves have sufficed to support the rise of civilizations. A mere dozen species account for over 80% of the modern world's annual tonnage of all crops. Those dozen blockbusters are the cereals wheat, corn, rice, barley, and sorghum, the pulse soybean, the roots or tubers potato, manioc, and sweet potato, the sugar sources sugarcane and sugar beet, and the fruit banana. Cereal crops alone now account for more than half of the calories consumed by the world's human populations. With so few major crops in the world, all of them domesticated thousands of years ago, it's less surprising that many areas of the world had no wild native plants at all of outstanding potential. Our failure to domesticate even a single major new food plant in modern times suggests that ancient peoples really may have explored virtually all useful wild plants and domesticated all the ones worth domesticating. Yet some of the world's failures to domesticate wild plants remain hard to explain. The most flagrant cases concern plants that were domesticated in one area but not in another. We can thus be sure that it was indeed possible to develop the wild plant into a useful crop, and we have to ask why that wild species was not domesticated in certain areas. A typical puzzling example comes from Africa. The important cereal sorghum was domesticated in Africa's Sahel zone, just south of the Sahara. It also occurs as a wild plant as far south as southern Africa, yet neither it nor any other plant was cultivated in southern Africa until the arrival of the whole crop package that Banta farmers brought from Africa north of the equator 2,000 years ago. Why did the native peoples of southern Africa not domesticate sorghum for themselves? Equally puzzling is the failure of people to domesticate flax in its wild range in Western Europe and North Africa, or einkorn wheat in its wild range in the southern Balkans. Since these two plants were among the first 8 crops of the Fertile Crescent, they were presumably among the most readily domesticated of all wild plants. They were adopted for cultivation in those areas of their wild range outside the Fertile Crescent as soon as they arrived with the whole package of food production from the Fertile Crescent. Why, then, had peoples of those outlying areas not already begun to grow them of their own accord? Similarly, the 4 earliest domesticated fruits of the Fertile Crescent all had wild ranges stretching far beyond the eastern Mediterranean, where they appear to have been first domesticated. The olive, grape, and fig occurred west to Italy and Spain and northwest Africa, while the date palm extended to all of North Africa and Arabia. These 4 were evidently among the easiest to domesticate of all wild fruits. Why did peoples outside the Fertile Crescent fail to domesticate them, and begin to grow them only when they had already been domesticated in the eastern Mediterranean and arrived thence as crops? Other striking examples involve wild species that were not domesticated in areas where food production never arose spontaneously, even though those wild species had close relatives domesticated elsewhere. For example, the olive Olea europaea was domesticated in the eastern Mediterranean. There are about 40 other species of olives in tropical and southern Africa, southern Asia, and eastern Australia, some of them closely related to Olea europaea, but none of them was ever domesticated. Similarly, while a wild apple species and a wild grape species were domesticated in Eurasia, there are many related wild apple and grape species in North America, some of which have in modern times been hybridized with the crops derived from their wild Eurasian counterparts in order to improve those crops. Why, then, didn't Native Americans domesticate those apparently useful apples and grapes themselves? One can go on and on with such examples. But there is a fatal flaw in this reasoning. Plant domestication is not a matter of hunter-gatherers domesticating a single plant and otherwise carrying on unchanged with their nomadic lifestyle. Suppose that North American wild apples really would have evolved into a terrific crop if only Indian hunter-gatherers had settled down and cultivated them. But nomadic hunter-gatherers would not throw over their traditional way of life, settle in villages, and start tending apple orchards unless many other domesticable wild plants and animals were available to make a sedentary food-producing existence. Apples or Indians? Competitive with a hunting-gathering existence. How, in short, do we assess the potential of an entire local flora for domestication? For those Native Americans who failed to domesticate North American apples, did the problem really lie with the Indians or with the apples? In order to answer this question, we shall now compare three regions that lie at opposite extremes among centers of independent domestication. As we have seen, one of them, the Fertile Crescent, was perhaps the earliest center of food production in the world, and the site of origin of several of the modern world's major crops and almost all of its major domesticated animals. The other two regions, New Guinea and the eastern United States, did domesticate local crops, but these crops were very few in variety, only one of them gained worldwide importance. And the resulting food package failed to support extensive development of human technology and political organization as in the Fertile Crescent. In the light of this comparison, we shall ask, did the flora and environment of the Fertile Crescent have clear advantages over those of New Guinea and the eastern United States? One of the central facts of human history is the early importance of the part of Southwest Asia known as the Fertile Crescent. That area appears to have been the earliest site for a whole string of developments, including cities, writing, empires, and what we term civilization. All those developments sprang, in turn, from the dense human populations, stored food surpluses, and feeding of non-farming specialists made possible by the rise of food production in the form of crop cultivation and animal husbandry. Food production was the first of those major innovations to appear in the Fertile Crescent. Hence, any attempt to understand the origins of the modern world must come to grips with the question why the Fertile Crescent's domesticated plants and animals gave it such a potent head start. Fortunately, the Fertile Crescent is by far the most intensively studied and best understood part of the globe as regards the rise of agriculture. For most crops domesticated in or near the Fertile Crescent, the wild plant ancestor has been identified, its close relationship to the crop has been proven by genetic and chromosomal studies, its wild geographic range is known. Its changes under domestication have been identified and are often understood at the level of single genes. Those changes can be observed in successive layers of the archaeological record, and the approximate place and time of domestication are known. Figure 8.1, the Fertile Crescent, encompassing sites of food production before 700 BC. Vantages and the resulting development of crops can be specified in much more detail for the Fertile Crescent. One advantage of the Fertile Crescent is that it lies within a zone of so-called Mediterranean climate, a climate characterized by mild, wet winters and long, hot, dry summers. That climate selects for plant species able to survive the long dry season and to resume growth rapidly upon the return of the rains. Many Fertile Crescent plants, especially species of cereals and pulses, have adapted in a way that renders them useful to humans. They are annuals, meaning that the plant itself dries up and dies in the dry season. Within their mere 1 year of life, annual plants inevitably remain small herbs. Many of them instead put much of their energy into producing big seeds, which remain dormant during the dry season and are then ready to sprout when the rains come. Annual plants therefore waste little energy on making inedible wood or fibrous stems, like the body of trees and bushes. But many of the big seeds, notably apples or Indians, those of the annual cereals and pulses, are edible by humans. They constitute 6 of the modern world's 12 major crops. In contrast, if you live near a forest and look out your window, the plant species that you see will tend to be trees and shrubs, most of whose body you cannot eat and which put much less of their energy into edible seeds. Of course, some forest trees in areas of wet climate do produce big edible seeds, but these seeds are not adapted to surviving a long dry season and hence to long storage by humans. A second advantage of the Fertile Crescent flora is that the wild ancestors of many Fertile Crescent crops were already abundant and highly productive, occurring in large stands whose value must have been obvious to hunter-gatherers. Experimental studies in which botanists have collected seeds from such natural stands of wild cereals, much as hunter-gatherers must have been doing over 10,000 years ago, show that annual harvests of up to nearly a ton of seeds per hectare can be obtained, yielding 50 kilocalories of food energy for only 1 kilocalorie of work expended. By collecting huge quantities of wild cereals in a short time when the seeds were ripe, and storing them for use as food through the rest of the year, some hunting-gathering peoples of the Fertile Crescent had already settled down in permanent villages even before they began to cultivate plants. Since Fertile Crescent cereals were so productive in the wild, few additional changes had to be made in them under cultivation. As we discussed in the preceding chapter, the principal changes, the breakdown of the natural systems of seed dispersal and of germination inhibition, evolved automatically and quickly as soon as humans began to cultivate the seeds in fields. The wild ancestors of our wheat and barley crops look so similar to the crops themselves that the identity of the ancestor has never been in doubt. Because of this ease of domestication, big-seeded annuals were the first, or among the first, crops developed not only in the Fertile Crescent but also in China and the Sahel. Contrast this quick evolution of wheat and barley with the story of corn, the leading cereal crop of the New World. Corn's probable ancestor, a wild plant known as teosinte, looks so different from corn in its seed and flower structures that even its role as ancestor has been hotly debated by botanists for a long time. Teosinte's value as food would not have impressed hunter-gatherers. It was less productive in the wild than wild wheat, it produced much less seed than did the corn eventually developed from it, and it enclosed its seeds in inedible hard coverings. For teosinte to become a useful crop, it had to undergo drastic changes in its reproductive biology, to increase greatly its investment in seeds, and to lose those rock-like coverings of its seeds. Archaeologists are still vigorously debating how. Many centuries or millennia of crop development in the Americas were required for ancient corn cobs to progress from a tiny size up to the size of a human thumb, but it seems clear that several thousand more years were then required for them to reach modern sizes. That contrast between the immediate virtues of wheat and barley and the difficulties posed by teosinte may have been a significant factor in the differing developments of New World and Eurasian human societies. A third advantage of the Fertile Crescent flora is that it includes a high percentage of hermaphroditic selfers, that is, plants that usually pollinate themselves but that are occasionally cross-pollinated. Recall that most wild plants either are regularly cross-pollinated hermaphrodites or consist of separate male and female individuals that inevitably depend on another individual for pollination. Those facts of reproductive biology vexed early farmers, because, as soon as they had located a productive mutant plant, its offspring would crossbreed with other plant individuals and thereby lose their inherited advantage. As a result, most crops belong to the small percentage of wild plants that either are hermaphrodites usually pollinating themselves or else reproduce without sex by propagating vegetatively. Thus, a high percentage of hermaphroditic selfers in the Fertile Crescent flora aided early farmers, because it meant that a high percentage of the wild flora had a reproductive biology convenient for humans. Selfers were also convenient for early farmers in that they occasionally did become cross-pollinated, thereby generating new varieties among which to select. That occasional cross-pollination occurred not only between individuals of the same species, but also between related species to produce interspecific hybrids. One such hybrid among Fertile Crescent selfers, bread wheat, became the most valuable crop in the modern world. Of the first 8 significant crops to have been domesticated in the Fertile Crescent, all were selfers. Of the 3 selfer cereals, among them einkorn wheat, emmer wheat, and barley, the wheats offered the additional advantage of a high protein content, 14%. In contrast, the most important cereal crops of Eastern Asia and of the New World, rice and corn, respectively, had a lower protein content that posed significant nutritional problems. Those were some of the advantages that the Fertile Crescent's flora afforded the first farmers. It included an unusually high percentage of wild plants suitable for domestication. However, the Mediterranean climate zone of the Fertile Crescent extends westward through much of southern Europe and northwest Africa. Apples or Indians. Figure 8.2, the world's zones of Mediterranean climate. There are also zones of similar Mediterranean climates in 4 other parts of the world: California, Chile, southwestern Australia, and South Africa. Yet those other Mediterranean zones not only failed to rival the Fertile Crescent as early sites of food production, they never gave rise to indigenous agriculture at all. What advantage did that particular Mediterranean zone of Western Eurasia enjoy? It turns out that it, and especially its Fertile Crescent portion, possessed at least 5 advantages over other Mediterranean zones. First, Western Eurasia has by far the world's largest zone of Mediterranean climate. As a result, it has a high diversity of wild plant and animal species, higher than in the comparatively tiny Mediterranean zones of southwestern Australia and Chile. Second, among Mediterranean zones, Western Eurasia experiences the greatest climatic variation from season to season and year to year. That variation favored the evolution, among the flora, of an especially high percentage of annual plants. The combination of these two factors, a high diversity of species and a high percentage of annuals, means that Western Eurasia's Mediterranean zone is the one with by far the highest diversity of annuals. The significance of that botanical wealth for humans is illustrated by the GE 111. Table 8.1 World Distribution of Large-Seeded Grass Species Area. Number of species. Table 12.1 of Mark Blumler's Ph.D. dissertation, Seed Weight and Environment in Mediterranean-type Grasslands in California and Israel, listed the world's 56 heaviest seeded wild grass species for which data were available. Grain weight in those species ranged from 10 milligrams to over 40 milligrams, about 10 times greater than the median value for all of the world's grass species. Those 56 species make up less than 1% of the world's grass species. This table shows that these prize grasses are overwhelmingly concentrated in the Mediterranean zone of Western Eurasia. Geographer Mark Blumler's studies of wild grass distributions. Among the world's thousands of wild grass species, Blumler tabulated the 56 with the largest seeds, the cream of nature's crop, the grass species with seeds at least 10 times heavier than the median grass species. Virtually all of them are native to Mediterranean zones or other seasonally dry environments. Furthermore, they are overwhelmingly concentrated in the Fertile Crescent or other parts of Western Eurasia's Mediterranean zone, which offered a huge selection to incipient farmers, about 32 of the world's 56 prize wild grasses. Specifically, barley and emmer wheat. The two earliest important crops of the Fertile Crescent rank respectively 3rd and 13th in seed size among those top 56. In contrast, the Mediterranean zone of Chile offered only 2 of those species, California and southern Africa just 1 each, and southwestern Australia none at all. That fact alone goes a long way toward apples or Indians. Explaining the course of human history. A third advantage of the Fertile Crescent's Mediterranean zone is that it provides a wide range of altitudes and topographies within a short distance. Its range of elevations, from the lowest spot on Earth to mountains of 18,000 feet, ensures a corresponding variety of environments, hence a high diversity of the wild plants serving as potential ancestors of crops. Those mountains are in proximity to gentle lowlands with rivers, floodplains, and deserts suitable for irrigation agriculture. In contrast, the Mediterranean zones of southwestern Australia and, to a lesser degree, of South Africa and Western Europe offer a narrower range of altitudes, habitats, and topographies. The range of altitudes in the Fertile Crescent meant staggered harvest seasons. Plants at higher elevations produce seeds somewhat later than plants at lower elevations. As a result, hunter-gatherers could move up a mountainside harvesting grain seeds as they matured, instead of being overwhelmed by a concentrated harvest season at a single altitude, where all grains matured simultaneously. When cultivation began, it was a simple matter for the first farmers to take the seeds of wild cereals growing on hillsides and dependent on unpredictable rains, and to plant those seeds in the damp valley bottoms, where they would grow reliably and be less dependent on rain. The Fertile Crescent's biological diversity over small distances contributed to a fourth advantage: its wealth in ancestors not only of valuable crops but also of domesticated big mammals. As we shall see, there were few or no wild mammal species suitable for domestication in the other Mediterranean zones of California, Chile, southwestern Australia, and South Africa. In contrast, for species of big mammals, the goat, sheep, pig, and cow were domesticated very early in the Fertile Crescent, possibly earlier than any other animal except the dog anywhere else in the world. Those species remain today four of the world's 5 most important domesticated mammals. But their wild ancestors were commonest in slightly different parts of the Fertile Crescent, with the result that the 4 species were domesticated in different places, sheep possibly in the central part, goats either in the eastern part at higher elevations or in the southwestern part, pigs in the north-central part, and cows in the western part, including Anatolia. Nevertheless, even though the areas of abundance of these 4 wild progenitors thus differed, all 4 lived in sufficiently close proximity that they were readily transferred after domestication from one part of the Fertile Crescent to another, and the whole region ended up with all 4 species. Agriculture was launched in the Fertile Crescent by the early domestication of 8 crops, termed founder crops. Those 8 founders were the cereals emmer wheat, einkorn wheat, and barley, the pulses lentil, pea, chickpea, and bittervetch, and the fiber crop flax. Of these 8, only 2, flax and barley, range in the wild at all widely outside the Fertile Crescent and Anatolia. 2 of the founders had very small ranges in the wild, chickpea being confined to southeastern Turkey and emmer wheat to the Fertile Crescent itself. Thus, agriculture could arise in the Fertile Crescent from domestication of locally available wild plants, without having to wait for the arrival of crops derived from wild plants domesticated elsewhere. Conversely, 2 of the 8 founder crops could not have been domesticated anywhere in the world except at the Fertile Crescent, since they did not occur wild elsewhere. Thanks to this availability of suitable wild mammals and plants, early peoples of the Fertile Crescent could quickly assemble a potent and balanced biological package for intensive food production. That package comprised 3 cereals as the main carbohydrate sources, 4 pulses, with 20-25% protein, and 4 domestic animals as the main protein sources, supplemented by the generous protein content of wheat, and flax as a source of fiber and oil. Eventually, thousands of years after the beginnings of animal domestication and food production, the animals also began to be used for milk, wool, plowing, and transport. Thus, the crops and animals of the Fertile Crescent's first farmers came to meet humanity's basic economic needs: carbohydrate, protein, fat, clothing, traction, and transport. A final advantage of early food production in the Fertile Crescent is that it may have faced less competition from the hunter-gatherer lifestyle than that in some other areas, including the Western Mediterranean. Southwest Asia has few large rivers and only a short coastline, providing relatively meager aquatic resources. One of the important mammal species hunted for meat, the gazelle, originally lived in huge herds but was overexploited by the growing human population and reduced to low numbers. Thus, the food production package quickly became superior to the hunter-gatherer package. Sedentary villages based on cereals were already in existence before the rise of food production and predisposed those hunter-gatherers to agriculture and herding. In the Fertile Crescent, the transition from hunting-gathering to food production took place relatively fast. As late as 9000 BC, people still had no crops and domestic animals and were entirely dependent on wild foods, but by 6000 BC some societies, apples or Indians, were almost completely dependent on crops and domestic animals. The situation in Mesoamerica contrasts strongly. That area provided only 2 domesticable animals, whose meat yield was far lower than that of cows, sheep, goats, and pigs, and corn, Mesoamerica's staple grain, was, as I've already explained, difficult to domesticate and perhaps slow to develop. As a result, domestication may not have begun in Mesoamerica until around 3500 BC. Those first developments were undertaken by people who were still nomadic hunter-gatherers, and settled villages did not arise there until around 1500 BC. In all this discussion of the Fertile Crescent's advantages for the early rise of food production, we have not had to invoke any supposed advantages of Fertile Crescent peoples themselves. Indeed, I am unaware of anyone's even seriously suggesting any supposed distinctive biological features of the region's peoples that might have contributed to the potency of its food production package. Instead, we have seen that the many distinctive features of the Fertile Crescent's climate, environment, wild plants, and animals together provide a convincing explanation. Since the food production packages arising indigenously in New Guinea and in the eastern United States were considerably less potent, might the explanation there lie with the peoples of those areas? Before turning to those regions, however, we must consider 2 related questions arising in regard to any area of the world where food production never developed independently or else resulted in a less potent package.
First, do hunter-gatherers and incipient farmers really know well all locally available wild species and their uses, or might they have overlooked potential ancestors of valuable crops? Second, if they do know their local plants and animals, do they exploit that knowledge to domesticate the most useful available species, or do cultural factors keep them from doing so? As regards the first question, an entire field of science, termed ethnobiology, studies people's knowledge of the wild plants and animals in their environment. Such studies have concentrated especially on the world's few surviving hunting-gathering peoples, and on farming peoples who still depend heavily on wild foods and natural products. The studies generally show that such peoples are walking encyclopedias of natural history, with individual names for as many as 1,000 or more plant and animal species, and with detailed knowledge of those species' biological characteristics, distribution, and potential uses. As people become increasingly dependent on domesticated plants and animals, this traditional knowledge gradually loses its value and becomes lost, until one arrives at modern supermarket shoppers who could not distinguish a wild grass from a wild pulse. Here's a typical example. For the last 33 years, while conducting biological exploration in New Guinea, I have been spending my field time there constantly in the company of New Guineans who still use wild plants and animals extensively. One day, when my companions of the 4 tribe and I were starving in the jungle because another tribe was blocking our return to our supply base, a 4-man returned to camp with a large rucksack full of mushrooms he had found, and started to roast them. Dinner at last. But then I had an unsettling thought: what if the mushrooms were poisonous? I patiently explained to my 4 companions that I had read about some mushrooms being poisonous, that I had heard of even expert American mushroom collectors dying because of the difficulty of distinguishing safe from dangerous mushrooms, and that although we were all hungry, it just wasn't worth the risk. At that point my companions got angry and told me to shut up and listen while they explained some things to me. After I had been quizzing them for years about names of hundreds of trees and birds, how could I insult them by assuming they didn't have names for different mushrooms? Only Americans could be so stupid as to confuse poisonous mushrooms with safe ones. They went on to lecture me about 29 types of edible mushroom species, each species name in the 4 language, and where in the forest one should look for it. This one, the tanti, grew on trees, and it was delicious and perfectly edible. Whenever I have taken New Guineans with me to other parts of their island, they regularly talk about local plants and animals with other New Guineans whom they meet, and they gather potentially useful plants and bring them back to their home villages to try planting them. My experiences with New Guineans are paralleled by those of ethnobiologists studying traditional peoples elsewhere. However, all such peoples either practice at least some food production or are the partly acculturated last remnants of the world's former hunter-gatherer societies. Knowledge of wild species was presumably even more detailed before the rise of food production, when everyone on Earth still depended entirely on wild species for food. The first farmers were heirs to that knowledge, accumulated through tens of thousands of years of nature observation by biologically modern humans living in intimate dependence on the natural world. It therefore seems extremely unlikely that wild species of potential value would have escaped the notice of the first farmers. The other, related question is whether ancient hunter-gatherers and farmers 116 apples or Indians similarly put their ethnobiological knowledge to good use in selecting wild plants to gather and eventually to cultivate. One test comes from an archaeological site at the edge of the Euphrates Valley in Syria, called Tel Abu Huraira. Between 10,000 and 900 BC, the people living there may already have been residing year-round in villages, but they were still hunter-gatherers. Crop cultivation began only in the succeeding millennium. The archaeologists Gordon Hillman, Susan College, and David Harris retrieved large quantities of charred plant remains from the site, probably representing discarded garbage of wild plants gathered elsewhere and brought to the site by its residents. The scientists analyzed over 700 samples, each containing an average of over 500 identifiable seeds belonging to over 70 plant species. It turned out that the villagers were collecting a prodigious variety of plants identified by their charred seeds, not to mention other plants that cannot now be identified. Were those naive villagers collecting every type of seed plant that they found, bringing it home, poisoning themselves on most of the species, and nourishing themselves from only a few species? No, they were not so silly. While 157 species sounds like indiscriminate collecting, many more species growing wild in the vicinity were absent from the charred remains. The 157 selected species fall into three categories. Many of them have seeds that are non-poisonous and immediately edible. Others, such as pulses and members of the mustard family, have toxic seeds. The toxins are easily removed, leaving the seeds edible. A few seeds belong to species traditionally used as sources of dyes or medicine. The many wild species not represented among the 157 selected are ones that would have been useless or harmful to people, including all of the most toxic weed species in the environment. Thus, the hunter-gatherers of Tel Abu Hurera were not wasting time and endangering themselves by collecting wild plants indiscriminately. Instead, they evidently knew the local wild plants as intimately as do modern New Guineans, and they used that knowledge to select and bring home only the most useful available seed plants. But those gathered seeds would have constituted the material for the unconscious first steps of plant domestication. My other example of how ancient peoples apparently used their ethnobiological knowledge to good effect comes from the Jordan Valley in the 9th millennium BC, the period of the earliest crop cultivation there. The valley's first domesticated cereals were barley and emmer wheat, which are still among the world's most productive crops today. But, as at Tel Abu Hurera, hundreds of other seed-bearing wild plant species must have grown in the vicinity, and 100 or more of them would have been edible and gathered before the rise of plant domesticated. What? Was it about barley and emmer wheat that caused them to be the first crops? Were those first Jordan Valley farmers botanical ignoramuses who didn't know what they were doing? Or were barley and emmer wheat actually the best of the local wild cereals that they could have selected? Two Israeli scientists, Ofer Bar Yosef and Mordecai Kislev, tackled this question by examining the wild grass species still growing wild in the valley today. Leaving aside species with small or unplantable seeds, they picked out 23 of the most palatable and largest seeded wild grasses. Not surprisingly, barley and emmer wheat were on that list. But it wasn't true that the 21 other candidates would have been equally useful. Among those 23, barley and emmer wheat proved to be the best by many criteria. Emmer wheat has the biggest seeds and barley the second biggest. In the wild, barley is one of the 4 most abundant of the 23 species, while emmer wheat is of medium abundance. Barley has the further advantage that its genetics and morphology permit it to evolve quickly the useful changes in seed dispersal and germination inhibition that we discussed in the preceding chapter. Emmer wheat, however, has compensating virtues. It can be gathered more efficiently than barley, and it is unusual among cereals in that its seeds do not adhere to husks. As for the other 21 species, their drawbacks include smaller seeds, in many cases lower abundance, and in some cases their being perennial rather than annual plants, with the consequence that they would have evolved only slowly under domestication. Thus, the first farmers in the Jordan Valley selected the 2 very best of the 23 best wild grass species available to them. Of course, the evolutionary changes in seed dispersal and germination inhibition would have been unforeseen consequences of what those first farmers were doing. But their initial selection of barley and emmer wheat rather than other cereals to collect, bring home, and cultivate would have been conscious and based on the easily detected criteria of seed size, palatability, and abundance. This example from the Jordan Valley, like that from Tel Abu Hurera, illustrates that the first farmers used their detailed knowledge of local species to their own benefit. Knowing far more about local plants than all but a handful of modern professional botanists, they would hardly have failed to cultivate any useful wild plant species that was comparably suitable for domestication. We can now examine what local farmers, in 2 parts of the world with indigenous but apparently deficient food production systems compared to that of the Fertile Crescent, actually did when apples or Indians. More productive crops arrived from elsewhere. If it turned out that such crops did not become adopted for cultural or other reasons, we would be left with a nagging doubt. Despite all our reasoning so far, we would still have to suspect that the local wild flora harbored some ancestor of a potential valuable crop that local farmers failed to exploit because of similar cultural factors.
These two examples will also demonstrate in detail a fact critical to history, that indigenous crops from different parts of the globe were not equally productive. New Guinea, the largest island in the world after Greenland, lies just north of Australia and near the equator. Because of its tropical location and great diversity in topography and habitats, New Guinea is rich in both plant and animal species, though less so than continental tropical areas because it is an island. People have been living in New Guinea for at least 40,000 years, much longer than in the Americas, and slightly longer than anatomically modern peoples have been living in Western Europe. Thus, New Guineans have had ample opportunity to get to know their local flora and fauna. Were they motivated to apply this knowledge to developing food production? I mentioned already that the adoption of food production involved a competition between the food production and the hunting-gathering lifestyles. Hunting-gathering is not so rewarding in New Guinea as to remove the motivation to develop food production. In particular, modern New Guinea hunters suffer from the crippling disadvantage of a dearth of wild game. There is no native land animal larger than a 100-pound flightless bird and a 50-pound kangaroo. Lowland New Guineans on the coast do obtain much fish and shellfish, and some lowlanders in the interior still live today as hunter-gatherers, subsisting especially on wild sago palms. But no people still live as hunter-gatherers in the New Guinea highlands. All modern highlanders are instead farmers who use wild foods only to supplement their diets. When highlanders go into the forest on hunting trips, they take along garden-grown vegetables to feed themselves. If they have the misfortune to run out of those provisions, even they starve to death, despite their detailed knowledge of locally available wild foods. Since the hunting-gathering lifestyle is thus non-viable in much of modern New Guinea, it comes as no surprise that all New Guinea highlanders and most lowlanders today are settled farmers with sophisticated systems of food production. Extensive, formerly forested areas of the highlands were converted by traditional New Guinea farmers to fenced, drained, intensively managed field systems supporting dense human populations. Surrounding New Guinea were still occupied exclusively by hunter-gatherers, so this ancient agriculture must have developed independently in New Guinea. While unequivocal remains of crops have not been recovered from those early fields, they are likely to have included some of the same crops that were being grown in New Guinea at the time of European colonization and that are now known to have been domesticated locally from wild New Guinea ancestors. Foremost among these local domesticates is the modern world's leading crop, sugarcane, of which the annual tonnage produced today nearly equals that of the number 2 and number 3 crops combined. Other crops of undoubted New Guinea origin are a group of bananas known as Australamusa bananas, the nut tree Canarium indicum, and giant swamp taro, as well as various edible grass stems, roots, and green vegetables. The breadfruit tree and the root crops yams and taro may also be New Guinean domesticates, although that conclusion remains uncertain because their wild ancestors are not confined to New Guinea but are distributed from New Guinea to Southeast Asia. At present we lack evidence that could resolve the question whether they were domesticated in Southeast Asia, as traditionally assumed, or independently or even only in New Guinea. However, it turns out that New Guinea's biota suffered from 3 severe limitations. First, no cereal crops were domesticated in New Guinea, whereas several vitally important ones were domesticated in the Fertile Crescent, Sahel, and China. In its emphasis instead on root and tree crops, New Guinea carries to an extreme a trend seen in agricultural systems in other wet tropical areas, whose farmers also emphasized root crops but did manage to come up with at least 2 cereals. A likely reason for the failure of cereal agriculture to arise in New Guinea is a glaring deficiency of the wild starting material. Not one of the world's 56 largest seeded wild grasses is native there. Second, the New Guinea fauna included no domesticable large mammal species whatsoever. The sole domestic animals of modern New Guinea, the pig and chicken and dog, arrived from Southeast Asia by way of Indonesia within the last several thousand years. As a result, while New Guinea lowlanders obtain protein from the fish they catch, New Guinea highland farmer populations suffer from severe protein limitation, because the staple crops that provide most of their calories are low in protein. Taro, for example, consists of barely 1% protein, much worse than even white rice, and far below the levels of the Fertile Crescent's wheats and pulses. Apples or Indians. Children in the New Guinea highlands have the swollen bellies characteristic of a high bulk but protein-deficient diet. New Guineans old and young routinely eat mice, spiders, frogs, and other small animals that peoples elsewhere with access to large domestic mammals or large wild game species do not bother to eat. Protein starvation is probably also the ultimate reason why cannibalism was widespread in traditional New Guinea highland societies. Finally, in former times New Guinea's available root crops were limiting for calories as well as for protein, because they do not grow well at the high elevations where many New Guineans live today. Many centuries ago, however, a new root crop of ultimately South American origin, the sweet potato, reached New Guinea, probably by way of the Philippines, where it had been introduced by Spaniards. Compared with taro and other presumably older New Guinea root crops, the sweet potato can be grown up to higher elevations, grows more quickly, and gives higher yields per acre cultivated and per hour of labor. The result of the sweet potato's arrival was a highland population explosion. That is, even though people had been farming in the New Guinea highlands for many thousands of years before sweet potatoes were introduced, the available local crops had limited them in the population densities they could attain, and in the elevations they could occupy. In short, New Guinea offers an instructive contrast to the Fertile Crescent. Like hunter-gatherers of the Fertile Crescent, those of New Guinea did evolve food production independently. However, their indigenous food production was restricted by the local absence of domesticable cereals, pulses, and animals, by the resulting protein deficiency in the highlands, and by limitations of the locally available root crops at high elevations. Yet New Guineans themselves know as much about the wild plants and animals available to them as any peoples on Earth today. They can be expected to have discovered and tested any wild plant species worth domesticating. They are perfectly capable of recognizing useful additions to their crop larder, as is shown by their exuberant adoption of the sweet potato when it arrived. That same lesson is being driven home again in New Guinea today, as those tribes with preferential access to introduced new crops and livestock expand at the expense of tribes without that access or willingness. Thus, the limits on indigenous food production in New Guinea had nothing to do with New Guinea peoples, and everything with the New Guinea biota and environment. Ported independent domestication of local wild plant species. However, early developments are much better understood for the eastern United States than for New Guinea. The crops grown by the earliest farmers have been identified, and the dates and crop sequences of local domestication are known. Well before other crops began to arrive from elsewhere, Native Americans settled in eastern U.S. river valleys and developed intensified food production based on local crops. Hence they were in a position to take advantage of the most promising wild plants. Which ones did they actually cultivate, and how did the resulting local crop package compare with the Fertile Crescent's founder package? It turns out that the eastern U.S. founder crops were 4 plants domesticated in the period 2500–1500 BC, a full 6,000 years after wheat and barley domestication in the Fertile Crescent. A local species of squash provided small containers, as well as yielding edible seeds. The remaining 3 founders were grown solely for their edible seeds. But 4 seed crops in a container fall far short of a complete food production package. For 2,000 years those founder crops served only as minor dietary supplements, while eastern U.S. Native Americans continued to depend mainly on wild foods, especially wild mammals and waterbirds, fish, shellfish, and nuts. Farming did not supply a major part of their diet until the period 500–200 BC, after 3 more seed crops had been brought into cultivation. A modern nutritionist would have applauded those 7 eastern U.S. crops. All of them were high in protein, 17–32%, compared with 8–14% for wheat, 9% for corn, and even lower for barley and white rice. 2 of them, sunflower and sumpweed, were also high in oil. Sumpweed, in particular, would have been a nutritionist's ultimate dream, being 32% protein and 45% oil. Why aren't we still eating those dream foods today? Alas, despite their nutritional advantage, most of these eastern U.S. crops suffered from serious disadvantages in other respects. Goosefoot, knotweed, little barley, and maygrass had tiny seeds, with volumes only 1/10 that of wheat and barley seeds. Worse yet, sumpweed is a wind-pollinated relative of ragweed, the notorious hay fever-causing plant. Like ragweeds, sumpweed's pollen can cause hay fever where the plant occurs in abundant stands. If that doesn't kill your enthusiasm for becoming a sumpweed farmer, Be aware that it has a strong odor objectionable to some people and that handling it can cause skin irritation. Mexican crops finally began to reach the eastern United States by trade routes. Apples or Indians. After AD 1. Corn arrived around AD 200, but its role remained very minor for many centuries. Finally, around AD 900 a new variety of corn adapted to North America's short summers appeared, and the arrival of beans around AD 1100 completed Mexico's crop trinity of corn, beans, and squash. Eastern U.S. farming became greatly intensified, and densely populated chiefdoms developed along the Mississippi River and its tributaries. In some areas the original local domesticates were retained alongside the far more productive Mexican trinity, but in other areas the trinity replaced them completely. No European ever saw sumpweed growing in Indian gardens, because it had disappeared as a crop by the time that European colonization of the Americas began, in AD 1492. Among all those ancient eastern U.S. crop specialties, only two have been able to compete with crops domesticated elsewhere and are still grown today. Our modern acorn squashes and summer squashes are derived from those American squashes domesticated thousands of years ago. Thus, like the case of New Guinea, that of the eastern United States is instructive. A priori, the region might have seemed a likely one to support productive indigenous agriculture. It has rich soils, reliable moderate rainfall, and a suitable climate that sustains bountiful agriculture today. The flora is a species-rich one that includes productive wild nut trees. Local Native Americans did develop an agriculture based on local domesticates, did thereby support themselves in villages, and even developed a cultural florescence around 200 BC, AD 400. They were thus in a position for several thousand years to exploit as potential crops the most useful available wild plants, whatever those should be. Nevertheless, the Hopewell florescence sprang up nearly 9,000 years after the rise of village living in the Fertile Crescent. Still, it was not until after AD 900 that the assembly of the Mexican crop trinity triggered a larger population boom, the so-called Mississippian florescence, which produced the largest towns and most complex societies achieved by Native Americans north of Mexico. But that boom came much too late to prepare Native Americans of the United States for the impending disaster of European colonization. Food production based on eastern U.S. crops alone had been insufficient to trigger the boom, for reasons that are easy to specify. The area's available wild cereals were not nearly as useful as wheat and barley. Native Americans of the eastern United States domesticated no locally available wild pulse, no fiber crop, no fruit or nut tree. They had no domesticated animals at all except for dogs, which were probably domesticated elsewhere in the Americas. It's also clear that Native Americans of the eastern United States were not overlooking potential major crops among the wild species around them. Even 20th century plant breeders, armed with all the power of modern science, have had little success in exploiting North American wild plants. Yes, we have now domesticated pecans as a nut tree and blueberries as a fruit, and we have improved some Eurasian fruit crops by hybridizing them with North American wild relatives. However, those few successes have changed our food habits far less than Mexican corn changed food habits of Native Americans in the eastern United States after AD 900. The farmers most knowledgeable about eastern U.S. domesticates, the region's Native Americans themselves, passed judgment on them by discarding or de-emphasizing them when the Mexican Trinity arrived. That outcome also demonstrates that Native Americans were not constrained by cultural conservatism and were quite able to appreciate a good plant when they saw it. Thus, as in New Guinea, the limitations on indigenous food production in the eastern United States were not due to Native American peoples themselves, but instead depended entirely on the American biota and environment. We have now considered examples of three contrasting areas, in all of which food production did arise indigenously. The Fertile Crescent lies at one extreme, New Guinea and the eastern United States lie at the opposite extreme. Peoples of the Fertile Crescent domesticated local plants much earlier. They domesticated far more species, domesticated far more productive or valuable species, domesticated a much wider range of types of crops, developed intensified food production and dense human populations more rapidly, and as a result entered the modern world with more advanced technology.
more complex political organization, and more epidemic diseases with which to infect other peoples.
We found that these differences between the Fertile Crescent, New Guinea, and the eastern United States followed straightforwardly from the differing suites of wild plant and animal species available for domestication, not from limitations of the peoples themselves.
When more productive crops arrived from elsewhere,
local peoples promptly took advantage of them, intensified food production, and increased greatly in population. By extension, I suggest that areas of the globe where food production never developed indigenously at all, California, Australia, the Argentine Pampas, Western Europe, and so on, may have offered even less in the way of wild plants and animals suitable for domestication than did New Guinea,
apples, or Indians.
And the eastern United States, where at least a limited food production did arise. Indeed, Mark Blumler's worldwide survey of locally available large-seeded wild grasses mentioned in this chapter, and the worldwide survey of locally available big mammals to be presented in the next chapter, agree in showing that all those areas of non-existent or limited indigenous food production